is related to the classical solution of Dirac equation. So we just have a couple of more identities, and these are actually probably the most useful ones. And they're about the completeness of the positive frequency and the negative frequency solutions. Okay, let me first bring this down. Right. So, and this is very definitely haunted. Do
you have anything heavy you could just like put on the...
Does anyone have a copy of Peskin?
Yeah, I actually do.
Okay, let's try this first. Peskin might not like that. So we are talking about anti-gravity today. So these are very useful. These are called spin sums. So let me call that. This is a nice blackboard. And if you take the U spinner, which corresponds, as we shall see, to particles, and do an outer product. So this is actually an outer product because this is, and the sum should be over S. Because this is a column matrix and this is a row matrix, so this object is a 4x4 matrix. This is a statement of completeness of these guys on the positive frequency space of solutions. And then we have a similar spin sum for the V spinners. So now we have introduced all the elements to write down the general plane wave solution of Dirac equation. So the general plane wave solutions. And they are given by, we have an integral over the momentum, the Lorentz invariant measure. We have an additional spin degree of freedom, so we have to sum over that. And here is the spinner. And the Fourier coefficients, these are BS, P. These are the basis waves, but psi is not required to be real. So it has another part. Oh, that's nice. So this is a different Fourier coefficient. Okay, so, and then we have the conjugate spinner, which is similar to here you have a U bar, so that means there's a gamma 0 multiplying it from right then we have ds star of p e plus I p dot x plus v bar s of p c of s of p minus I p dot x. Okay, so so that completes our discussion for the classical spinors. Okay. Now, let us talk about the symmetries of the Dirac theory. So recall Noether's theorem. Suppose you have a variation of your fields, and these are global infinitesimal variations, and they are of this form. So phi a are your fields, and you make some small transformations of the fields where the parameters of the transformations do not depend on space-time points. That's what we mean by global. And there's some function of the fields themselves, which are written here as xa of phi. So these are global transformations. And suppose under this transformation, your Lagrangian changes by some for divergence of some four-dimensional vector. And in such a way that the action remains invariant. So we're assuming that the boundary condition that we impose on f is such that the action will remain invariant. In other words, f will go to 0 at minus t infinity to plus t infinity, or when you go to infinite regions of space. If this is true, then the integral of delta L of all over space-time can be transformed into a surface integral using the generalization of Gauss's theorem, and then that surface integral can be ignored. So it's only when the Lagrangian changes, the change of the Lagrangian is of this form, that the action will still remain invariant. Of course, it may happen that under this transformation, the Lagrangian doesn't change. In that case, the right-hand side is 0. The Noether's theorem tells us that for each of these transformations, so for each parameter of the transformation, there is a conserved current, J mu, and the form of the conserved current is given by this. So there's an implicit sum over A here. And it also follows that because it's conserved, it means that its four-dimensional divergence is 0. Then there is a charge Q that you can define as the spatial integral over the 0th component of your conserved current. In some sense, the charge density, J0 is your charge density. And then this equation implies that Q is a constant of motion. Okay, so this is, I think you met this in the first part of this course. So I'm just reminding you. And now let's look at some applications of this to the Dirac theory. So let us remind ourselves what the Dirac Lagrangian is, the free Lagrangian. And then, number one, the internal global phase rotation. So these are transformations in which you multiply psi of x by a phase which depends on some parameter alpha, where alpha is some constant. And the fact that alpha is a constant, not a function of space-time, is what it means for this transformation to be global. And then psi bar of x then transforms psi bar of x e to the power minus I alpha. This is just a phase, so it doesn't matter if I write this on the left-hand side or the right-hand side, but I'm just writing it because later we'll see a transformation where the argument in the exponential will actually be a matrix. Okay? But in this case, it doesn't matter. And also, when you come to standard model, you will find that there's a generalization of this transformation in which instead of one spinor field, you consider like a whole columns of different spinor fields, and there will be some matrix acting on that. In that case, the conjugate transformation would be the complex conjugate of the matrix, actually the Hermitian conjugate of the matrix acting on the right. So, yeah?
So you don't change the gamma matrices?
No.
Then I'd like to ask whether is the representation invariance for the Dirac algebra a symmetry of the Dirac theory?
Representation of the, you mean this one?
No, I mean for going from the representation of the change of phi to phi conjugate.
Right.
You just could the gamma zero there, the implicit gamma zero.
Oh, right, yes, yeah. So, yeah, in this case, it doesn't matter, right? Because it's just a phase. But in the case of, hang on to that thought because this will become relevant in one of the examples that I'll do, after this. So, okay, so now because this is just a constant. So the derivative acting on it doesn't do anything, and this is just a phase, so it just commutes with all the gamma matrices. It should be obvious that this is invariant. However, for the sake of finding out what the current is, we can just work out what delta of psi is. And the Lagrangian, of course, doesn't change. So that is 0 in this case. And then the current is, the conserved current is simply given by this. Now we can verify quite easily that this is 0. But to verify, you have to use the equations of motion. And I will leave it as an exercise for you to do this. These are the kind of questions that I might ask you to do in the interview. It'll turn out that this current is the conserved charge associated with this charge. When you quantize it, is actually going to be the electric charge. So number 2, there's a symmetry of the Dirac-Lagrangian, which is only there when in the limit where m goes to 0. So take the massless case. And the symmetry in that case is psi x goes to e to the power I alpha gamma 5 of psi x. So now this object is a non-trivial matrix. Then psi bar of x, which as we know is psi dagger of x times gamma 0, this will transform as psi dagger of x e to the power minus I alpha gamma 5 dagger, psi 0, right? However, gamma 5 is permission. So we can get rid of this. And gamma 5 anticommutes with gamma 0. So if you pull this guy out in this side, what will happen is that in the expansion of this, everywhere, where there's a, even power of gamma, gamma squares to 1, so that the sign of those terms will not change. But everywhere there's an odd power of gamma, because gamma squares to 1 is just gamma 5. Because gamma 5 will anticommute with gamma 0, those terms will change signs, right? So this will become gamma of x e to the power plus I alpha of gamma 5, right? So here, the sign here, and here they're the same. And now, if you look at the kinetic term has this gamma mu. So now this guy will pick up e to the power I alpha gamma 5. This guy will pick up this guy, but the same thing, but over here, right? And because gamma 5 anticommutes with gamma mu by the same logic that we just used, when you pull one of these exponential factors through, it'll flip sign again, and therefore they will cancel. Okay? So we can see that in the m equals to 0 limit, there is an additional symmetry. And this symmetry is sometimes called the chiral symmetry. And it's easy to show that the current associated with this chiral symmetry is this guy. Okay. Now, if you were to quantize this theory, and this is something you will see in your QFT3 course, you'll see that quantum effects will actually break the symmetry in the sense that classically you have this, but when quantum effects are taken into account, this is no longer true. The right-hand side will be non-zero. So that you will see in your later course, and that is an example of what is known as an anomaly, where a classical symmetry gets broken by quantum effects. Okay, so
is that a spontaneous or explicit breaking?
that's neither. An explicit breaking is something where you actually put a small term in your Lagrangian to break a symmetry. A spontaneous symmetry breaking is a symmetry where it's a symmetry of your Lagrangian, but it's not a symmetry of the vacuum state.
But the loop terms break this symmetry,
right? Right. So the loop terms will break. So I don't think you can call. I don't think it's right to classify them either as spontaneous or explicit. In a way, you can think of it as an explicit symmetry breaking, because another way of looking at it is to say that you quantize a theory, and then you have, typically there are some, you have to add what are known as counter terms to regulate to renormalize a theory. And what happens is that the symmetry that you had in the original Lagrangian, you can show that there is no way for that symmetry to be manifested in whatever counter term you add to make the theory finite. So then, in that sense, those counter terms are the one which break that symmetry. So from that point of view, you're right, it could be seen as an explicit symmetry breaking. But I think a lot of times when we say explicit symmetry breaking, we mean that we are adding some term in the classical action, which can be seen as a perturbation, which breaks the original symmetry. So, okay, so other important symmetries of the Dirac Lagrangian. Translational symmetry. So the Dirac Lagrangian doesn't have any explicit dependence on space or time coordinate. So if we make an infinitesimal, well, even a finite shift in space or time, our spinor field you can change it. We can do a Taylor expansion. So here we are assuming that alpha is infinitesimal, A is infinitesimal. Right. So delta of psi then is A mu, delta mu psi. In a similar way, change in the Lagrangian is this. So, and then there's a corresponding change in delta of psi bar, which has the same form, and this allows you to write down your forecurrent there's a corresponding term for the bar. Then minus A mu of L. Now, the way that we have chosen our Lagrangian means that this term is actually 0. Now, if you now put in what the values of these, delta L by delta mu psi A and psi A bar are, then we get, okay, do I have to hold you down? Slightest perturbations will actually make it go up. Okay, so J mu has this form. So there's actually 4 conserved currents, because in writing the delta L, we took all 4 transformations, space translation and time translation. So, so we can knock off these A mu's, and so in the end we get 4 currents. So this is the space-time index. So this is the, denoting this is a 4 vector. But for each A mu, we have 1 conserved current, and this is given by so correspondingly there are 4 conserved charges. So we take the 0th component of each of this current and integrate them over all of space. And this is the energy momentum 4 vector. Okay. So there is another important conserved class of conserved charge, which I'm not going to do, but I'm going to leave that as an exercise. It's actually quite an involved exercise, but it's worth doing. It's one of those things which are good for the soul, which is the conserved charges that arise from conservation under Lorentz transformation. So under Lorentz transformation, can anyone tell me how many conserved charges should we get? 6. What are these 6? Anyone else? Can somebody tell me what these 6 are? Can you tell me what 3 of these are? Three components of an angular momentum, right? So those correspond to the rotation matrices. But what are the other 3?
They live on the phase space?
The what?
They live on the phase space?
No, they correspond to boosts, right?
Yes, but that's not a conserved.
Right. It's basically that's that's the motion of the center of mass. Those are the other 3 components. Okay. Because they're not conserved in that sense. So okay. All right. So.
They're not conserved.
Well, it's conserved in the sense that the direction is the center of mass moves with some constant velocity, right? So it's conserved in that sense, right?
So in what sense is it not conserved? By Noether's theorem, that gives you a Noether's conserved course.
Yeah, right. No, I mean it is conserved, but it's usually not. I think I would say they're conserved. Yeah. So yeah. Okay, so this brings us to a close regarding the discussion about classical spinners. So we'll now move on to our next topic, which would be the quantization of spinners. Okay. 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 So there's an important theorem in Konopilti. It's called the spin statistics theorem. And in 3+1 dimensions, this implies that half integer particles, half integer spin particles satisfy Fermi-Dirac statistics and integer spin particles satisfy Bose-Einstein statistics. in 2 + 1 dimensions, the spin statistics theorem actually allows for more general kinds of particles. And those particles are known as anyons, and in condensed matter systems, you actually see those things. So one of the consequences of the spin statistic theorem is the stability of free particle Hamiltonian. So, once you have you write down a Lagrangian, the Lagrangian that we wrote down for Dirac spinners, once we quantize it in such a way that it satisfies the Fermi-Dirac statistics, then the Hamiltonian that we will derive from the Lagrangian will be bounded from below. Yeah?
Please, I'm wondering, is there a physical reason why the spin statistics theorem holds? Like a physical argument you can give for why the theorem actually exists or holds?
Physical argument. For the covariant case, for the relativistic case, nothing comes to mind. For quantum field theories, which are not relativistic, in that case, there is no such theorem, but there's still a spin statistics connection. And that connection is that if you impose, hang on, let me check. Right, so in condensed matter physics, if you impose that fermions, they satisfy, half integer particles satisfy the Fermi-Dirac statistics, and integer spin particles satisfy Bose-Einstein statistics, then it turns out that you get stability of your Hamiltonian. So I think that fact actually is also generalizes to relativistic cases. For relativistic systems such as this one, if you were to quantize your system such that you get Bose-Einstein statistics, you can show that your Hamiltonian is not, bounded from below. So I think that is quite a good physical argument. It's kind of a negative argument, but that's a good argument why the spin statistics theorem should hold. But it's actually quite an involved and intricate theorem. So but that's probably a very big simplification of that. Okay. So as I said to Eugene's question, if you impose the positivity of Hamiltonian, then the spin statistics connection, this connection is something that follows, right? And it follows, this is particularly important for condensed matter applications where there is no, Lorentz invariant. So I should probably say spin statistics theorem in 3 + 1 dimension means that for relativistic QFTs, half integer particles, that this must be true. But for non-relativistic QFTs, by imposing the positivity, one way of imposing the positivity of the Hamiltonian is to actually, make this connection. Okay. Okay. This is just to motivate the fact that when we quantize our Dirac spinner today, that we are going to use anti-commutator rather than commutator. When you saw the quantization of the Klein-Gordon field, Dan used commutators, but for the Dirac field, we shall use anti-commutators to quantize. Schwarz has, in his book, consequence of what would happen if you quantize that theory using commutators, and he shows that you get Hamiltonians which are not positive, and all other kinds of inconsistencies. Okay. So I wrote earlier the classical expression for psi of x. But let me quickly write what the quantum expression of this guy is. So when we quantize, we replace the Fourier coefficient we had by an operator. So now B is an operator. And sometimes in quantum mechanics books, people will write a caret to denote it's an operator, but we'll use B's so many times that it's very inconvenient to write caret. So this is an operator now, not a function. Just hang on 1 second. Let me just finish this. And Vs of P, now this is, instead of star, this is yes, CJ?
No, I was just wondering about why there's a positive P dot x and then minus.
About this positive and negative? Oh, remember when we, so these are 4 vectors. So when I write P dot x, I mean, P mu, x mu. And when I write this P, this is a 3 vector, okay? And remember when we found the Dirac solution of the classical Dirac equation, we said, okay, we are going to take psi for some momentum P as U of P e to the power I x dot P. It's exactly that thing, but now we are summing over, we are actually summing over all of P. So for each P, there's a linearly independent solution to the Dirac equation, okay? And each of the P's also satisfy the mass shell condition because, as you know, the solution to the Dirac equation must satisfy the Klein-Gordon equation, right?
I was expecting maybe there'll be a minus on that one and a plus.
Oh, would there be a minus? Oh, maybe. Yes. Thank you. It's yeah, okay. Okay. I think in the notes I've made a...
No, it's not a mistake because it's with 3 vectors here. In the notes, it's not in the Heisenberg picture.
Oh, yes, exactly, yes.
Mm-hmm.
Yes. Thank you, thanks. I completely forgot about that. So I'm actually looking at a very particular time slice here. So I'm fixing T to be 0. Because the quantization that I'm going to do that in the Schrodinger picture. And then in the Heisenberg picture, this guy will have a time evolution, where, it'll have a time dependence. But in the Schrodinger picture, I'm just fixing the operator to some time, and then I'm going to use the anti-commutator to quantize. Thank you. And then that would be great. Okay. Thanks for pointing that out. So psi dagger will be similar. And I'm not going to write it out, but you'll have some U dagger here. And here you'll have a B dagger. You'll have a V dagger here, and you'll have a C here. And here you will have minus I P dot x plus I P dot x. Okay. So our conjugate momentum can then compute then instead of the usual commutation relationships, we're going to impose equal time anti-commutation relationship. I'm just putting in the factor of h bar for a moment. And now if you put in the expression for pi, the factor of I, the factors of I drop out from both sides. Okay. And we also impose that all components, the anti-commutative with psi vanish, all components of psi bar, anti-commutative with psi bar vanish. Okay. And then there is about a page of algebra where you use some properties of the classical spinors, do some relabeling, do some delta function integrals, then show that these things imply that BSP, BR, P prime, their anticommutator is 2 pi cubed to EP delta SR delta cubed P minus P prime. And so in other words, these are kind of fermionic creation and annihilation operator, and so are the C's. Okay. And the way we have normalized things will imply that the normalization of the states will be Lorentz invariant. And it also means that all other anti-commutators such as these guys there are a few others, such as B and C, and yeah, those things are also zero. So also let me just write this BC, B dagger C. Okay. Oh, I actually have something computed out. Yeah, let's do this because it's good to do this calculation once in your life and then just forget about it. And then, and then not do them ever again. So. And in my experience, if I tell you to do something, you'll probably do only like 10% of what I tell you to do. It's like, but there are exceptions. All right, what we are trying to compute is this thing. Okay. So this is going to be boring, so I apologize in advance. So I'm doing the Fourier expansion. There will be two sums and two spinners. Right. And now we are actually writing explicitly the matrix element of the spinners. P1, comma. So we are just verifying that those commutators do give what we claim that it does. And then e to the power I P1 dot x minus I P2 dot y. So that's one term. There will be a term between B's and C's, and those, as we said here, are 0. And there will be another term So I will give you another, so I'll do this exercise, but I'll give you another one to do at home, which is the more interesting one. Maybe I should have done that one. But anyway, it's too late. All right. And so this thing is then 2 pi cubed 2EP1 delta SR Dirac delta of P1 minus P2. And similarly, this is the same thing. So we can replace those things and use the delta function to do one of these P integrals. And we can also use the Kronecker delta to do one of these S sums. And then when we do the spin sum, right. So once we have done one of the spin sums, what it does is that the delta sets this R to S, and here it also sets this R to S. And then we have one more spin sum left. And then the identity that I wrote earlier, the two identities I wrote about how the spin sums give you the operator on the positive, like, let me just write them. Convenient that way. So we use those to get rid of the spinner factors. And then once you've done that, you have one of the momentum left. None of the spin sums left because we have used up all those spin sums. But we have gamma 0 P0 minus gamma I Pi plus M times gamma 0. And we have the AB component of this guy, e to the power ip dot x minus y. And from this term, we get, I'm just writing this out explicitly because there will be cancellations which will require me to do that. And the gamma 0 comes from the fact that we had just u dagger and v dagger here. And to use the spin sums, we needed u bar and v bar. So we had to insert a square of a gamma 0 as an identity. So that's where this gamma 0 comes from. And we have the same guy over here. Yeah?
I'm sure I understand what this sub AB means when it's placed next to a bracket.
Oh, it means that this is a 4x4 matrix. I'm taking the AB component of it.
But those NV are not spinner indices, right? They're field indices.
No, AB are just the spinner indices. Like over here, you see, we had U spinner. This is about a spinner. We took the A index of this, and here we took the B index of this, right?
Okay.
And that's because for the spinner psi, we took the Ath component of the spinner psi. In the first psi dagger, we took the B component, right?
So they're not different fields. They're, well, like, okay, I guess.
Well, psi is a column matrix.
Yeah.
Psi dagger is a row matrix. Sure. I'm just taking one component of these things. The anti-commutation relationship that we're imposing, it has is not on this, on these indices, right? So it's, we in some sense we're adding a new index by making them operators. Okay. Are people clear why this is AB here? Okay. And we have the same exponential factor here, but here you saw that the signs were actually opposite, and we can do that by taking P2 minus P. And is that true? I think so. Anyway, so once you've done that, you can just cancel these guys, but these two things don't cancel. And then after, right, exactly, yeah. So here, so just one subtle point is that the first term had the sign in the exponential was opposite relative to the sign of the exponential here, right? But if you expand p slash, then in both terms you should have a minus sign here, right? But in the second term, what we have done is that we have taken the 3 momentum p and replaced it by minus of p. And because there's an odd power of p here, we can absorb that minus p and basically get back the same measure. But the net effect is that wherever we had the 3 vector p, they switched their sign. So this guy switched their sign, and this guy also switched their signs to become exactly the same. And that allowed us to cancel these two terms and these two terms. Okay. So yeah, these are the kind of steps that you will need to perform every time you do these computations. They're not difficult, they're just tedious. Okay, so in the end we get d cubed of p 2 pi cubed 2 of EP, and we have gamma naught P naught, and oh yeah, so this gamma naught will multiply this gamma naught to give me an identity matrix. So we have delta AB as a result. So we have I P dot x minus y. So when we do now we can do the momentum integral, and then we have delta AB delta cubed x minus y. So we have just established that imposing those anti-commutation relationships is consistent with the anti-commutation relationship we imposed here. Okay. Okay, so you probably are familiar with the next thing I'm going to tell you, but it's still worth doing, is to kind of see how anti-commutation relationships lead to Fermi-Dirac statistics. So we have some, say, vacuum state, and we apply B dagger on this state, and then twice. So we create some, what I will claim is a two-particle state, with momentum P1, spin state S1, momentum P2, spin state S2. Right. Now, according to Fermi-Dirac statistics, if we now exchange these two particles, if we take P1, S1 and exchange it with P2, S2, then we should get the same state but with a minus sign. Right? So that is the essence of Fermi-Dirac statistics. And of course, it's easy to see that this happens here because these two guys anti-commute. So if we now use the anti-commutation relationship, we get B of S2 of P2, B of S1 of P1 acting on the vacuum. And this just gives us P2 S2, P1 S1 with the minus sign. So it's kind of very trivial to see that anti-commutation relationships do lead to Fermi-Dirac statistics. Okay. So we can now work out what the Hamiltonian is. The quantum Hamiltonian. And there's a very small surprise there. So for the Hamiltonian, we have to get the Hamiltonian from the Lagrangian, we have to make a Legendre transformation. And that means this thing. And when you work this out, it's just a spatial component that enters the Hamiltonian. Now, right. So now you can expand psi and psi bar, and you can use the Dirac equation for each of the individual spinner components. So U of S e to the power minus I p dot x equals to 0, or v of s e to the power plus I p dot x is 0. So you can use these, and then some of the spinner identities which I've written out, and I'm not going to write this out, and do probably a few pages of calculation. So I did it a couple of years ago. So I'm not going to, I didn't do it last night or anything. But when you actually do these things, you get an expression from the Hamiltonian, which is almost what you expect, because you'd expect that with two kinds of creation and annihilation particles, you'll get two kinds of, you'll get energy stored in two kinds of particles, right? So you'd expect that you'd get a number operator for particle species A and number operator for particle species B, right? But if you do the naive thing, what you get is get a sum over the spin states, and you get B dagger R P B R of P. Then you get a minus sign. And then, if you use the anti-commutation relationship for this thing, you pick up a delta function. And then, as a result, you get sum over R. You get B dagger R of P, B R of P plus C dagger R of P, CR of P, and then you get the 0-point energy, and what is interesting is that you get in front of the 0-point energy a minus sign. Okay? So this is the 0-point energy. And of course, this is infinite. And in the scalar field theory case, you found that you had another 0 it came with a plus sign. So that this is something interesting to note about fermions, is that their 0 points energy have an opposite sign compared to scalar. So now imagine if you had two complex scalar fields, so that the number of degrees of freedom in your complex case was equal to the number of degrees of freedom in the spinner's field here. And you did this calculation, and you did the same calculation. The 0-point energy that you would get from the scalar field would actually cancel out this 0-point energy. Okay? So you may have heard of supersymmetric theories. In supersymmetric theories, the energy of the vacuum is automatically 0 because the number of degrees of freedom in the bosonic sector and the fermionic sector are equal. But what is so this is kind of a trivial observation, but what is interesting in supersymmetric theories is that a lot of the divergences one sees at one loop or higher loop, a lot of them actually cancel out in supersymmetric theories. Okay, yeah.
Are you putting the equation of motion into the Hamiltonian?
Yes, because I will have to use, I don't recall the details of doing this calculation. I did it a couple of years ago, but yes, you actually have to expand this out. The identities that you have to use are there in the notes.
Mm-hmm. No, I'm just wondering, because isn't the Hamiltonian supposed to give you the equation of motion? So if you impose that in the Hamiltonian, can you get any useful information from the Hamiltonian then, if you've already used it?
Right, so what I'm doing is I'm actually using the classical equations of motion. What the Hamiltonian will give you is the evolution of the quantum operators. Okay? So the traditional way of, so I'm starting back again. The traditional way of getting rid of this 0-point energy is to do what is known as a normal ordering of your operators. So you just subtract it, essentially. Because we're dealing with quantum field theory on flat space-time, we can do that. In curved space-time, this will actually is not very straightforward. I will not go into it, but there you have to actually deal with the vacuum energy, because the vacuum energy will have an effect on Einstein's equations. So it'll have a back reaction on the geometry of space-time, and then the subtraction that you do, you'll have to justify, why, you'll have to do more justification for your subtraction. So the fermionic normal ordering is defined in the following way. Suppose you have a creation operator and an annihilation operator. So this is a creation operator, and this is an annihilation operator. And normal ordering means taking the annihilation operator to the right of the creation operators. But because they're fermionic, you actually have to put a minus sign if you anti-commutate inside the normal ordering. So if these guys were bosonic operators, or one of them were bosonic, then of course this minus sign would not be there. No? You could just write it like that. And once you've written it like that, this is now in normal order form, so you can get rid of the normal ordering. Okay. So now consider a one-particle state. And then if you apply your Hamiltonian on this one particle state, using the algebras that we are using, doing a little bit of algebra, you can show that this actually gives you there should be a K here, what you expect. So I'm not going to go through the algebra. The details are given in the notes. And what is interesting, and this is something that I would like you guys to do at home, is to work out what the normal ordering of the charge operator is. So recall that the charge operator is the zeroth component of the conserved current. Now, if you do the calculation, a calculation analogous to the calculation we did for the commutator and also the expression I wrote down for the Hamiltonian, you will find another surprise here. So this is the number operator for the first type of particle. But the number operator of the second type of particle comes with a minus sign in front. So this means that the total number of particles of type B and the total number of particles of type C is not conserved. What is conserved is their difference.
That's the normal order one?
Yeah. They're normal order, right? So this tells us that the interpretation of particle B and particle C should be that of particle and antiparticle. Okay? So what is conserved in, if you had two real scalar fields, what would be conserved is the total number of particles, right? But in a complex scalar field and also in a complex spinor field, the conserved charge has a minus sign. So that's important. So in other words, Q is not a positive definite or a negative definite quantity. Okay? So if your state doesn't have any C type of particle, you basically have just you just count the number of particles in your state, and if your state doesn't have B type of particle, you count the number of particles in the C state. So so the interpretation of the B dagger as creating the particle and C dagger as creating the antiparticle follows from this expression. Okay.
If you did normal order, you would get an infinite constant, like in the case of.
I think so. Yeah, I don't exactly recall, but I think so. You might get an infinite constant. Yes. And then you'd have to deal with probably the charge of the vacuum or something like. But I haven't done this calculation recently, so I don't exactly recall. So yeah, find it out. So in the Heisenberg picture, then, our operator is the Schrödinger picture operator. So this is something you actually derive using the Heisenberg equation of motion. So now the sign is flipped, and now this is a 4-vector contraction. And now this is also a 4-vector contraction. And sometimes the part of psi that contains the annihilation operator, we call it psi plus, and the part that contains that creation operator, we call psi minus. So this contains the annihilation operator for particles. This contains the creation operator for antiparticles. You might say, why do we write plus? The plus refers to the fact that these guys are the positive frequency solutions. And minus refers to the fact that this is a negative frequency solution. Of course, positive frequency solution has minus in the exponential, and negative frequency has plus. Just to make things more interesting. Okay, in the last 10 minutes, I will just start something, maybe not be able to finish, which is an important point, is causality and the Feynman propagator. So we are dealing with local quantum field theories. And in local quantum field theories, the statement of causality is that if you have two observables, O1 and O2, then they're local functions of space-time. Then causality implies that their commutator is 0 at space-like intervals. Okay, so if this is your space-time, if one of your operators is at this point, O1, and the other operator is outside his light cone, O2, then their commutator must vanish. But if O2 is inside the light cone, then they need not vanish. The commutator need not vanish. In scalar field theories, what you do is that the quantization conditions allow for stuff like this to be true for space-like separation. And because all your observables are made out of these guys, imposing this implies that this is always true. Because you can always decompose the operator, the left-hand side, in terms of commutators of the component fields. However, if you compute the commutator of Fermi fields, in general, this is not true. So the way out of this puzzle is to observe that all the observables made out of fermionic fields, so observables of fermionic fields have the form that they are bilinears of the fermionic field. So there'll be a psi and psi bar and some gamma matrix object. This could be gamma 5, it could be gamma mu, it could be an antisymmetric combination of gamma, but that's the generic form that they will have. So this would be the form of our observable in a fermionic theory. So if you could have, ensure that this is true, then we would be in business, because the commutator of a bilinear of fermionic fields can be decomposed in terms of anti-commutator of the component fields. Okay? And this is something that we used, say, when we worked out the algebra of n and a dagger. Remember, this was given by this. Although A is, we imposed anti-commutation relationship on A dagger. So what was N? N was A dagger A. So we actually decompose the left-hand side in terms of anti-commutators of A and A dagger, and you can do that just by doing by simple algebra. Then you can actually, so the upshot is that this will actually allow you to satisfy this kind of relationship. Okay? So let us show that this is actually true for the free fermion. So if you compute, I've given you the expression for psi. The expression of psi bar is just you can just figure it out from this expression. And then you can say, okay, what if I compute this thing in general using those commutation relationship? Then you can show that this has the form of the Dirac operator, where here x means this is a derivative with respect to x, not y, acting on some fields which you probably saw in your scalar field theory part, but if you haven't, that's fine too. So these d's are functions which have the form like this. Now, note that if you're outside the light cone, that is x and y, x minus y is space-like, then you can always go to a reference frame where x0 and y0 are the same. They're simultaneous. Okay. Then this three momentum, this dot product just becomes a three momentum dot product. So the sign of this exponential factor in this guy and the sign of the exponential factor in this guy, they're opposite. But remember our old trick where we replace the three momentum p by its minus of three momentum. We can do it in the second term, and that will flip this sign. And because of this minus sign, these two guys will cancel. So we see that for outside the light cone, for space-like separation, this object is indeed 0.
Well, where these equations came from?
I just calculated it. I just used these expressions, used the commutation relationships and everything, and all the machineries of the Dirac equation and everything to compute this. But this is not 0 in general, but what I've just argued is it's 0 for space-like separation. Okay? So I have 1 minute, and let me just tell you something which I'll come back to next time. And the idea is that what is the consistent definition for the time ordering for fermions? And yes, you've guessed it, you need to introduce a minus sign. But recall that time ordering for bosons meant that phi of x1, phi of x2, if x1 0 was greater than x2 0, and phi of x2, phi of x1 is if x2 0 is greater than x1 0. In the case of fermions, this won't work because suppose you had two fermionic fields which anti-commuted. So all fermionic fields anti-commute, but I'm assuming that they don't have a delta function. So we could, because they anti-commute by assumption, we could always write it like this. Now suppose that x naught is greater than y naught. Then if we apply the time ordering operator to both sides, then on the left-hand side, this is already time ordered, so we can write this as psi alpha of x, chi beta of y. But this is not time ordered, sorry. So and the same here, minus. But this is not time ordered. So if we assume our same definition of the time ordering, sorry, there's a minus sign here, then there would be a minus sign psi alpha of x, chi beta of y, which would mean that this is 0. In general, there is no reason for this to be 0. So the fact that fermionic fields in general anti-commute means that for the time ordering, we cannot adopt the time ordering for bosons. We actually have to introduce a time ordering which actually has a minus sign, and that's where we'll start next time. Okay. All right. Thank you.